Today we're going to talk about probability with permutations. We began to talk about this in the last lesson informally, but today we will put more focus on it. So let's just review permutations. Suppose we consider the letters in the word parabola. There are 8 letters. Using all 8 letters, how many arrangements are possible? Now, whenever we have the word arrangement, we think of order. Order matters. So recall from a previous lesson, to get the number of different words, in quotes, that we could make from the letters in the word parabola, we consider the letters distinct. So there are 8 of them, and there are 8 factorial ways to do that. But one of the letter, the A's, repeat 3 times. So we divide by the extra permutations of the letters A as if they were distinct. So when we simplify this, we get 8 times 7 times 6 times 5 times 4 times 3 factorial over 3 factorial. And our answer for that problem will be, we'll leave it as a product, 8 times 7 times 6 times 5 times 4. We'll leave it like that. Okay, now in B, how many arrangements can have an A in the last position? Well, we have to be careful here. If we take out an A, now notice that here we have repeating letters. So if we take out an A and reserve it for the last position, there's only one way. So I'm going to write this down. Take out an A for the last position. But then there are 7 letters to arrange. That's one way. So there are 7 letters left with 2 A's that repeat. So the number of ways to arrange that would be 7 factorial divided by 2 factorial. And again, we could simplify that to 7 times 6 times 5 times 4 times 3. Do the 2 factorials divide through. Now, how many arrangements can have an A in the first and last positions? Well, okay, in the same way, we're going to take out an A, 2 A's, and reserve them for the first and last position. So take out an A for the first position. That's one way. Take out an A for the last position, which is one way. We have 6 different letters now that remain in 6 places. 6 different letters in 6 places. Because we used up 2 of the A's and there's 1 left over. So that's 6 factorial ways to arrange them. So the answer would be 1 times 1 times 6 factorial. So let's just put a box around our answers. Okay, so these are the total number of arrangements. This is when the last position has to be an A. And then finally, when the first and last positions are A. Okay, now what does this have to do with probability? It was 8, 7, 4. Supposing we were asked to find the probability of each of these events. Well, it's very important to analyze the number of ways that the event can occur divided by the total possible number of outcomes. So if we look at our do now, we basically found the probabilities. We just have to put them together. We noticed that the number of ways that we're given 8 letters, and they're all not different, and we want the last position to be an A, we found that the number of ways was 1 times 7 factorial over 2 factorial. Okay, and the total number of possible permutations that could be is 8 factorial over 3 factorial. And we would simplify that. Let's try E. In E, again, the denominator is still 8 factorial divided by 3 factorial, because this is the total number of ways we could arrange the letters in the word parabola. But the number of ways an A could be in the first and last position, we said was 1 times 6 factorial, and we would simplify these. So using what we've had in the do now, let's substitute. The denominators came out to be 8 times 7 times 6 times 5 times 4. And 7 factorial divided by 2 factorial, we said was 7 times 6 times 5 times 4 times 3. The 2 factorials divide through. And 6 factorial is just 6 times 5 times 4 times 3 times 2 times 1. And if we divide through, notice the 7s divide through, the 6 divides through, the 5 divides through, the 4 divides through, and the answer here is 3 out of 8. In this one, in E, the 6s divide through, the 5s divide through, and the 4 divides through. So we get 6 out of 56, it looks like. 6 out of 56. Which is the same as 3 over 28, even though I don't require simplifying it. Now, let's go back to the problems and think about it. Is there another way to get the 3 8s without using permutations? Well, in this particular problem, yes, because the 3 represents the number of A's we have, and 8 represents 8 letters in total. So this problem could have been done without permutations, even though I consider it more thorough. And let's look at the 3/28. Could we have gotten that in a different way? Well, if we think of it like drawing 2 cards out of a deck without replacement, the probability that the A is in the first place would be 3 out of 8. And the probability that the A is in the last place would be 2 out of 7. I want to go back to problem D and show you another way to do that, the more conventional way, and it might be easier for you. So let's revisit D. And the probability that A will be last, we can do it as follows. The denominator is still 8 factorial over 3 factorial. That's the number of ways to permute all letters in the word parabola. But think of it this way. We've got 8 letters. There would be 3 choices for the last letter to be an A. I mean, this is how we usually do it. We could choose from the 3 A's. Once that's chosen, 1 letter is taken up. So we've got 7 factorial letters to permute. So that would be 7 factorial. But because we're putting one of the 3 A's here, we can permute them in 3 factorial ways. So perhaps this would be easier to do permutations of this nature. In fact, it's up to you, whatever you like better. I like to count the number of possible ways to fill the restrictions and then consider what's left over and how to permute them. But here, the number of permutations among the 3 A's that we could pick would be 3 factorial, so we have to divide it here. Here, in the first one, in the original, we're picking an A, and we have 2 to permute. Okay, but here we have to permute all three. So, and if you look at the numerator, 7 factorial over 3 factorial times 3 is really 7 factorial over 2 factorial. So whichever way you look at it, it works. But just make sure that you're consistent in the procedure that you decide to use. We have a problem like this on the homework tonight, so be very careful. Let's take a look at another probability problem. Our standard deck of 52 cards. Suppose we pick 2 cards at random without replacement. Now, we did this in our last lesson, but let's look at it from a different perspective. So the probability of drawing 2 aces, what we did is we said, well, what's the probability that the first is an ace? And then the probability that the second is an ace, and we multiply. So there are 4 aces in the deck. So the first time we pick the card, there would be 4 out of 52. But once we pick the ace, then we have 3 left over. So we have 3 out of 51. So we think of these as separate little experiments combined. But if you take a look at it as a whole picture, what we're doing is we are considering 4 times 3, which is 4p2, and 52c1, which is 52p2. So another way to do this problem is to say that we are selecting 2 aces from 4 divided by the number of ways to select 2 cards from 52. So let's write this down. So this represents the number of ways to select 2 cards or 2 aces from 4. I should write 2 aces. 2 aces from 4. Or we could say, rather than select, we could say arrange 2 aces from 4 divided by the number of ways to arrange 2 cards from 52. So again, or to select 2 cards from 52. So we see that there's an overlap between permutations and probability, very big overlap. Now, the probability that the first card is the ace of hearts and the second is a black card in that order, we have to get the probability that the first is the ace of hearts times the probability that the second is a black card. So we think of these as 2 different experiments. So the probability that the first is the ace of hearts, well, that's really specific. There's only one way to get that. There's 1 card out of 52. But black cards, half the deck is black. We've got the spades and the clubs. So that's 27 out of... Now, remember, there are 26 black cards. The ace of hearts is already red, so we didn't affect the black cards, but there's 1 less card in the deck. So let's keep that in mind. That's a little trickier, I think. Can make my heart. Okay. Now, let's take a look at this again. Okay, now, if we look at it as 1 experiment, we could consider that this is equal to the number of ways to select the ace of hearts, which is 1p1, that's 1 way. The number of ways to select a black card, which would be 26p1, right? Because we're picking 1 card, divided by the number of ways to pick 2 cards from 52, which is 52p2. So here, notice that this tells us how many ways we could pick the ace of hearts, and that's just 1. There's 1 way. This represents the number of ways to pick 1 card out of the 26 black remaining. And this represents the total number of ways to pick 2 cards from 52. Again, we apply the counting principle because we're picking the ace of hearts and a black card. So again, we see how permutations come into the picture. But I personally prefer to do the problems this way. I find them easier. Be less than... Okay, now this is an interesting one that we can do without permutations, but let's look at it. A 3-digit numeral is formed by selecting at random from the digits 3, 4, 5, 6, and 7 with no repetitions. Okay, that's really important. What is the probability that the number value is less than 500? So first we have to consider the total number of ways we can form a 3-digit numeral here. So the number of ways to form a 3-digit numeral would be, well, there are 1, 2, 3, 4, 5 numbers to pick from. So the first one, there are 5 choices for the first, 4 for the second, and 3 for the third. But the number of ways the 3-digit numeral is less than 500, well, we have a restriction on the first spot. We still have to multiply by the counting principle. But if we want the number less than 500, then the first numeral must be either a 3 or a 4. We can't pick 5 because the digit after that would make it more than 500. So there are 2 ways to pick the first number, a 3 or a 4. Once that is chosen, it really doesn't matter what comes after it. So then we have 4 for the second and 3 for the third. So the probability that the 3-digit numeral is less than 500 would be the quotient of the 2. The number of ways that we could get a 3-digit numeral less than 500 divided by the total number of ways to get a 3-digit number. And if you look at that carefully, the answer is just 2 out of 5. Okay. I think this would be the easiest way to do it, but again, we can use permutation if you wish. We could think of it this way. The probability of a 3-digit numeral less than 500, okay? Rather than looking at it separately, we could think of it as one experiment so that there are, to make the first digit less than 5, there are 2 ways. So we have to pick one number from the 2. Think about how many numbers we have to pick and how many there are in the restriction. And then we have 4 numbers left over and we have 2 left over to pick, which would make a total of 3. Divided by the total number of ways to form a 3-digit number from 5. But if you look at it carefully, this is equivalent to this. So again, with permutations, we want to pick one digit, but there are 2 possible ways to pick it from, 2 possible options. And then we've already picked one. So we have 2 spots left over. Think about the spots. These are the spots. And how many do we have? 4. Divided by 5p3. Okay, so we see that we don't really need permutations to do these problems, but some problems do require permutation, like the next one. Okay, there's some probability problems concerning arrangements or permutations where we must use permutations, and that's illustrated in the next problem. Okay, so a numeral is formed by selecting from the digits 6, 7, 8, and 9. Okay, let me just write this and put a cloud over it. Without replacement. So we're forming a number from these 4 digits. what is the probability that the numeral has at least 3 digits? So for at least 3 digits, we want the probability that the number has 3 digits exactly, or 4 digits. We can't do anything else. At least 3 includes the 3, but goes up to the maximum. And in this case, we only have 4 digits. So let's consider the number of ways to get a 3-digit number. Well, that would be just 4 times 3 times 2. Because there are 4 choices for the first, 3 choices for the second, and 2 choices for the third. The number of ways to get a 4-digit number would be, again, 4 for the first, 3 for the second, 2 for the third, and 1 for the last. So we could express this as 4p3 over 4p4. Now, because we want the number to have 3 digits or 4 digits, we would probably add these two, because with or we add them. So the answer would be 4p3 plus 4p4. Or, in other words, 12 times 2 is 24, and 24 plus 24 is 48. Okay, now, the denominator, though, is not so simple, because here we have to determine the total number of possible arrangements. So, we have to, let's write this down. So, to determine the total number because notice we're forming any number by selecting the digits 6, 7, 8, and 9. But of course, we're focusing in on 3-digit numbers and 4-digit numbers. But if we pick numbers, we could pick 1 number, we could pick 2, we could pick 3 and 4. So determine the total number of possible arrangements from the given 4 digits. Okay, first we have to consider 1-digit numerals. But that's just 4, right? Or known as 4p1, 4 choices. 2-digit numerals, which is 4 times 3, known as 4p2. 3-digit numerals, which we already said was 4 times 3 times 2, which is 4p3, and 4-digit numerals, which is 4 times 3 times 2 times 1, which is 4p4. So here we have to add all these cases, because these are the total number of numerals we could make from the 4 digits, whether it's a 1-digit numeral, a 2-digit numeral, or a 3-digit numeral, or 4-digit numeral. So we have to add these, and this would represent the number of possible outcomes in our sample space. So the final answer would be the following. But then again, so if we wanted the probability of having at least a 3-digit numeral, we restrict the numerator to the number of arrangements for 3 from 4 digits and 4 from 4 digits. because that's at least 3. And then here we consider the total possible outcomes, whether we form a 1-digit numeral, a 2-digit numeral, a 3-digit numeral, or a 4-digit numeral. Now let's work this out. So if we work these out, I expanded the permutations. Notice that we factored out a 4 because there's a 4 in common everywhere. In the numerator, we could have factored out a 4 times 3, but it's okay. And when we compute, these 4's divide through, and when we compute, the answer comes out to be 12 out of 16, or 3/4. So here's an example where we have to consider many, many cases, and that's where we have to use permutations very carefully. And I'd like to end the lesson today with a little algebra problem. Suppose we have 5 white balls and K black balls in a jar. We don't know what K is. 2 balls are drawn without replacement, and the probability that one ball is white and the other is black is 10 out of 21. Find K. Pause the video and try it by yourself. Let's see if we come up with the same equation. So if one ball is white and the other is black, there are 2 possible outcomes that will give us that result. Either the first is white and the second is black, or the first is black or the second is white. And again, we add the probabilities. Now let's fill in the probabilities. So here's the equation I came up with. The probability that the first is white would be 5 white balls out of 5 plus K total balls in the jar. But once the white ball is picked, then there is 1 less ball in the jar, so that's 4 plus K. And the probability of picking the second ball black would be K out of 4 plus K. In the same way, the probability that the first ball is black would be K over K plus 5. And again, there's 1 less ball, so the denominator is 4 plus K, but there's still 5 white balls. And when we add these two, we get 10 out of 21. Lo and behold, we have a rational equation. Now, we could actually simplify this into the following. Because the denominators are the same, we could combine the numerators and get 10K over 5 plus K times 4 plus K equals 10 out of 21, since 5K plus 5K is 10K. But we've got to put these in parentheses, the binomials. All right, and to solve this, we can cross multiply. Notice I didn't multiply the 10 by 21 because I would like to divide each side by 10 and get 5 plus K times 4 plus K equals 21K. Now we end up solving a quadratic equation. So let's look at the next page. So I rearranged the terms in the binomials since addition's commutative, and I wrote K plus 5 times K plus 4 equals 21K. We multiplied it out, got the quadratic in standard form, and we could factor it into K minus 2 times K minus 10. And it looks like when we set each factor to 0, we have 2 possible answers. Can that be? Let's check it. So the 2 possibilities are 5 white and 2 black, or 5 white and 10 black. So let's see, does this probability work out? If we get a black white or a white black, let's try it. So we figured out the probabilities of the first white, the second black, or the first black, second white in each of these possible cases, and they seem to work. They work. They all come out to be a probability of 10 over 21. So the answer is that K can be 2 or 10, which is kind of different here than what we've been doing. I like this problem very much. Okay, everyone, have a wonderful day, and do the homework the same way.